Hello, I'm Jung Kyuri from the Department of Civil and Environmental Engineering at Yonsei University. I will begin my midterm presentation for the Smart City Infrastructure course. Today's content will be presented in the following order: REP VGG, REP LKNet, and Vision Language Model. Let's start with REP VGG. After VGG, multi-branch models such as ResNet were introduced. However, their complex structure made them harder to implement, less memory efficient, and slower in inference. RepVGG was proposed to address these challenges, complexity, and inference speed. On the left is the overall model architecture, and on the right is the rep block structure. As shown, the training and inference structure are different. During training, 3x3 and 1x1 convolutions with batch normalization and ReLU are used. During inference, it is simplified to a single 3x3 convolution with ReLU. The key point is that it used a multi-branch structure for training and a single branch for inference. Experiments shows that 3x3 kernels performs the best. RepVGG A and B differ in convolution and group convolution usage. Compared to other models, it achieves higher accuracy. Thanks to structure reparameterization, it is easy to optimize and suitable for mobile and real-time inference. Next is RepLKNet. Previous model used kernel no longer than 11 by 11. RepLKNet proposed that larger kernel may work better and shift focus from texture bias to shape bias. The image shows the overall structure of RepLKNet and the internal design of the RepLK block. Again, the training and inference structure differ slightly. This model used the GetLU activation function instead of ReLU, and very large kernels to capture entire object at once. On the left is the graph of the GetLU function. In performance comparison, RepLKNet tends to be on the left side, indicating a bias toward shape features over texture. Thanks to its larger kernel size, it can understand the object in one go, making suitable for high precision vision tasks such as autonomous driving or medical imaging. Let's now compare RepVGG and RepLKNet. As shown in the table, they differ in kernel size, reparameterization strategy, and activation function. RepVGG is optimized for mobile environment and real-time inference, while RepLKNet excels in high accuracy classification and complex structure prediction. To summarize, RepVGG is fast and lightweight, making it suitable for mobile applications. RepLKNet is slower and less mobile friendly, but achieves near SOTA performance. Now moving on to the Vision Language Model paper. Traditionally, PE compliance was checked using physical sensor attached to equipment. However, this approach was expensive and hard to scale in real industrial environments. So vision-based systems were developed, but they still had issues like complexity and poor generation. To solve this, VLMs were proposed. They were used Yellow World for object detection and OpenAI Clip for validating whether appropriate equipment is worn based on the environment. This image shows VLM compared to other SOTA model. VLM achieved comparable or better performance in both inference time and recognition accuracy. They can even analyze the material of PPE in diverse environments to determine whether it is properly worn. Through studying these models, I learned that deep learning isn't just about architecture competition, but about strategically solving problems. RepVGG shows that simple architecture can still perform well if we interpret it smartly. I realize it's important to understand not just how model works, but why it was designed that way. From now on, I will always ask myself that question when studying new architecture. Thanks for listening.